So, my name is Thijs Schreijer. I'm bugging everybody about it. My name is Thijs Schreijer. On GitHub you can find me under my username Kiske. I'm an engineer here at Mashape. And recently we've been working on load balancing. And what I'm going to talk about is just a general overview about how and what we implement, what we are implementing. So no code, just some diagrams. And to start off, let's see what it is that we do and what it is that we want to solve. Basically, our main product is Con, which is obviously the ape here in the middle. And it's a proxy based on OpenResty, of course. The whole often is pretty much about OpenResty. General setup where you find Con is load balancer in front, Con cluster behind, and from there on another set of load balancers, and then proxy on to the final service at the end. One of the things we wanted to do is that we wanted to cut out the second load balancer. Because basically Con already does a lot of stuff that has all the information that the load balancer needs as well, so we might as well do that in one go. One of the things we need to add to Con to do that is the notion of the individual, not just the targets, the upstreams, but individual services, which contain the services. So this is basically what we set out to solve. And then you would end up with a picture like this, which is a bit simpler and infrastructure speaking, it would reduce the latency of the entire request cycle. How would it work? Con is dynamically configured. So basically, whenever you add an upstream or add a new target, you put a call request towards Con, you configure it with a specific upstream URL. In this case, to provide a new service, to create a virtual service name that's actually embedded in the URL you provide, and then that service name will be on the fly by Con, be resolved to whatever you put it to load balance on. That's basically how it should work. A side effect of this is that you then can configure Con basically from microservices are quite often created as containerized applications, virtual machines, whatever. So they're easy to spin up and to spin down. And basically, once you spin it up, a single call request would immediately make Con serve traffic towards that new node. Likewise, when you're done and you're tearing it down, another single request would make it drop the traffic to the same node. So to make it a bit simple, let's just take an example on how to do this. Basically what we create is a ring balancer. You'll see in the next diagram. Simple example, 20 slots, and we have 4 targets, A, B, C, D, each getting 5 slots, which is, if they have equal weights, simple math. If you create a ring balancer, then you have 20 positions on the ring, obviously, and we're going to move the slots on there. What's specific is that there's an extra layer in between, and it's divided such that a specific target is connected to a specific slot, one of the 20 slots in this case, based on the weight. The higher the weight, the more slots it gets. Simple math. The second relation is between the slot and the position it gets on the wheel. And in this case it's a one-on-one and it's fully randomized. The reason to do this is that if you implement it, you get this. And now you can, in the most simple load balancing scheme moving around robin, you can simply traverse the wheel and be done with it. But obviously we want alternatives, which is, for example, consistent hashing. If you want to do consistent hashing, it basically means that based on specific properties of a request, we want to make sure that every time it hits, it ends up on the same backend server. Basically, what you try to do is to increase the cache hit ratio on the backend, so so the overall latency goes down again. That's basically what we try to do. So you calculate a hash, and it immediately points to one specific slot you're going to use to proxy to the upstream. One thing that we now run into is that cluster-wide consistent hashing. Notice that cluster-wide doesn't play well with randomness, because each ring is randomly created. If you have enough nodes in your cluster, there's too much randomness, so all the consistency is gone. So basically, we need to lock down on the randomness, because we cannot just let everybody create its own ring. So basically, the random data that's used to create a ring is part of the configuration data. And I think go back. One of the things you see here is the last one. Basically, we're doing another post request, so basically we're adding another entry. And it's basically because we keep track of all the changes. We don't keep track of which nodes we have, we keep track of the changes. So every node we add in a con cluster can replay the changes and end up with the same exact consistent hashing ring to make sure we remain consistent over the cluster without too much chattiness between the common clusters. So we can keep the latency down and the scaling optimal. There we go. Now in a simple setup where we would, the same example again, now we would add a target with, again, the same way. We would redistribute the slots. We're not going to recalculate the entire ring. We're just going to ask every target to relinquish, in this case, one slot. And the distribution is now slightly, if you look at the slots themselves, it's slightly odd. But because the ring is randomly distributed, it will be neatly fitted in with minimal cost in overhead. So we can still do the round robin thing and also consistent hashing. It has minimal impact. If you, for example, add 4 nodes and make a ring with 24 slots, then pretty much every slot would be reassigned, all consistency would be gone, and all the caches would have to reload in the backend. In this case, we can just the most minimal impact on our cache. To the same effect, we might have a situation where a node fails. Once again, in a cluster, especially if you have large clusters from, say, 30 nodes, 50, 40 nodes, whatever, we want to make sure that the chattiness in the cluster remains minimal. So every node will do its own health check. But then again, if there's a timing difference between the nodes, then we might get inconsistencies in the ring. So we need to take the system out without failing in our consistency. So in this case, because of the ring and the randomness in the ring, it provides us simple with the opportunity to, if it fails, we move on to the next slot. And because of the randomness in the ring, the fall through to the next slot will automatically have the exact same distribution with the exact same weight. No matter how you change it. And it all comes back to the initial relationship between the slot and the slot position to remain it at all time random. So, that was pretty much what we learned from how we were implementing it and some of the small things we ran into while creating a load balancer and how it fits with consistency and how you can solve without sacrificing too much. One of the bad things we run into is that the wheel size is fixed. So if you have too little slots, you scale too much, then if each machine gets like 2 or 3 slots, then your randomness is not well enough distributed. So once you change the size, then you're done, then all consistency goes. And the transaction list, of course, keeps growing. Especially with microservices, there might be a lot of cells being spun and spun out, and once in a while you need to clean up, and again, you lose all consistency. It is available on GitHub. That's what the branch is. It's still under construction. Groundwork's there, not complete. We hope to add an RC by the end of the month. So if you're interested in OpenResty balances, you're welcome to have a look. Questions?
How big are these registries in production systems?
How big they can be?
How big?
In general, I'd say for every target you have, at a minimum 50 slots. So you anticipate like 10 targets, and take 500, or probably even 1,000 slots. You need to make sure that the random distribution that it remains random based on the maximum expected size of your backend targets.
Why do you use hashing instead of just some table?
Why hashing? To make sure that we on the same input end up on the same server.
Right, but I mean, if you have like a search tree, then you can like assign some control to each node, and then you label things without having. I mean, you could add more nodes easily.
Okay. Let's discuss it again.
So why did you write it in Lua?
It's OpenResty, so we can write it on top of OpenResty in Lua. Basically, the entire code that will come is OpenResty Lua based. Obviously, some similarities, but that's the hashing algorithm is currently in OpenResty is also C based.
So like you choose the way to zero to your cloud.
The way to zero, yeah.
Then does it cause create something for everything else? Because now you're redistributing.
Yeah, if you would change the weight, the example I gave with adding one, it works the exact same around if you remove one. Like setting the weight to 0, then it will remove the 4 slots it has, and those will be reassigned to 0 for the example. It will be the exact same cost.
Yeah, I was curious if you have any plans to make this run faster, because one of the use cases I have in mind is you have a load balancer in front of conc, and then you have a bunch of services, and I assume you do round robin all that load balancer in front of conc.
Can you repeat the beginning of the question? I missed the start.
Yeah, so the question is actually if you have any plans to make this working in a distributed fashion, because right now this works on
What fashion?
distributed fashion.
Distributed fashion.
Yeah, because right now this works on a single node level, right?
No, the intent is to make it work on the entire conc cluster.
Okay, that was my question.
That was the whole idea. Otherwise, if you do it per cluster of per node, then the consistency doesn't make sense.
Is this code in the branch right now?
Yeah, code is currently in branch.
Okay.
How do you keep the transaction
Between the nodes. Basically, Consul uses a mechanism underlying uses serve by HashiCorp. And basically, whenever one of the nodes writes change in configuration, it sends an event across the cluster, and they validate their internal cache and do it for the database. But it's the general caching mechanism that Consul uses. And this just has to